Okay, should be recording. So then I'll turn things over to group 4.
Hello, everyone. Thank you for coming to our presentation today. We are Group 4. We're a group of 6 engineers comprised of Israel, Tim, myself, Patrick, Max, Drew, and Ryan, and we're here to present the Gator Pod today.
So a brief presentation outline. First, we'll go over our Hedgehog Concept, which are the 3 core values we kept in mind while creating this design. Next, we'll have a brief product overview, giving you the overall weight, cost, and dimensions of the CubeSat dispenser. Then we have a brief video product demonstration, and then key features, which shows what differentiates us from other CubeSat dispensers on the market. We have relevant subsystem analysis to prove that our concepts work. We then have the cost summary, which is the overall cost of the CubeSat dispenser and manufacturing times. And finally, a brief explanation on why we think you should pick up our CubeSat dispenser design.
So just to begin, we have our Hedgehog Concept, which is our 3 core values that we strive to maintain while we were developing this design. So first of all, we have innovation. So our primary goal behind this was to create, to meet the customer needs while also making our subsystems unique and creative. So we didn't want to just stick with the norm that, every dispenser did that we saw in our research. We wanted to do something unique and creative, and we were able to do that. Additionally, we wanted to make sure we have a positive impact on the world. So obviously the goal of this whole project from start to finish is to, advance space exploration. So we wanted to do that while also limiting environmental impact, both when it came to, wasted materials while it was being manufactured to, debris throughout the whole process, whether, here or in space. Additionally, we wanted to maximize the profit per subsystem. So we wanted to continue to, like I said, develop these unique subsystems that meet the customer needs while also being cost effective and not overwhelmingly expensive to fit in with that customer need of the cost requirement.
All right, and now on to the product overview. So you can see the dimensions of our product below. And while there wasn't a requirement on the actual size, we tried to minimize it to reduce cost, as well as be able to basically have more space inside the rocket fairing. And so our weight was just under the 5 kilogram requirement, and the cost was significantly under the $500,000 requirement. And lastly, we as a group strive to reduce parts, and our goal was initially 200, and we were able to come in at 161 total parts, including fasteners and small pieces like that. All right, and so I apologize because this is Zoom. You're probably going to watch this at about 1 frame a second, but this is our video. So let me play it. Oops. Let's see. Next slide. There we go. All right, and so some key features you can see in the back is our reinforced spring backing plate. This is where a lot of the force is going to be applied from launching the CubeSat. We also have a removable side to access the quick release, which you can see in the bottom picture here. And so some more key features of our design. So we have the control subsystem and a 28-volt power connector, as well as a check valve to release any excess pressure during launching. A very high fidelity transceiver that is able to both send and receive signals, as well as to control our pin puller mechanism, which you can see the buck converter below, which is the varying voltage output, as well as the single actuation system, which is controlled by the relay. And all of this is done by the transceiver. So it's a simple 3-piece design for the control subsystem.
So to begin with, we have our thermal venting subsystem, which utilized a check valve made of ABS plastic. So the thermal venting subsystem with the check valve meets several of our customer needs. The first of which is that it provides contamination protection. We were able to quantify this metric by minimizing the maximum effective vent ratio. We tried to keep it below 5,000 centimeters, and we were able to do that by achieving a value of 4089 centimeters. Additionally, the check valve meets the customer need of qualified for pre-launch purge and ascent profiles for all launchers. We were able to quantify this metric by minimizing the peak depressurization rate to negative 0.3 psi per second. We were able to get our design to have a depressurization rate of negative 0.39 psi per second. Additionally, the thermal venting subsystem meets the customer need of maintaining functionality through specified thermal environments for all launchers. This was quantified by minimizing the difference from average acceptable temperature between negative 10 and 40 degrees Celsius. We were able to achieve this with a temperature of 22 degrees Celsius. So the first metric that we quantified was with the maximum effective vent ratio. This was calculated by taking the internal volume and dividing it by the effective vent area, where we got a value of 4089 centimeters. Additionally, the thermal environment temperature was calculated using this heat transfer relation, which used the final and initial temperature, as well as the specific heat and total heat in the system. We were able to get a final temperature of 22 degrees Celsius. And then lastly, with the depressurization rate, we were able to calculate this using Bernoulli's equation. We had a couple assumptions, including that there was no external pressure, that also that the internal velocity was much less than the external velocity. With those assumptions, we were able to simplify the Bernoulli's equation down, as you can see below. We also used the ideal gas law. And together, we were able to calculate the pressure rate, solve it iteratively to be negative 0.39 psi per second.
So our next subsystem is the door subsystem. As shown in the video, it uses a pin puller that when a signal's sent to the pin puller, it contracts, allowing the torsion springs at the hinge of the door to open the door. And this subsystem meets 2 customer needs. The first one is customer need 19. The door must reliably open the door in a short period of time. We quantified this by minimizing the opening time to less than 2 minutes and maximizing reliability. Our design has an opening time of 0.18 seconds. The second customer need is need 20, and it's to qualify for pre-launch purge and ascent profiles for all launchers. We quantified this by maximizing the factor of safety to ensure like no debris being released. And our design has a factor of safety of 5. So the opening time was found as a function of the door angle, density, door velocity, door height, opening force, and point of force. And as mentioned previously, our opening time was 0.18 seconds. Some assumptions that were made for these calculations was the force acts perpendicular to the door, and the mass of the CubeSat is 15.455 kilograms, and the deployment velocity is 1.5 meters per second. The reliability was calculated as a function of the parts used in the subsystem, and the reliability for this subsystem is 99.94%.
So next we have the deployment subsystem. This utilized a compression spring to launch the CubeSat. The spring plate mates with the rail system that also mates with the CubeSat, and uses a mechanical pin puller to release the spring plate to allow the launching of the CubeSat. So the two customer needs that this subsystem met was the CubeSat must depart at a specified velocity. This velocity was found to be 1.5 meters per second, and we quantified this by saying we needed to maximize tunability to plus or minus 0.05 meters per second. Our design was is tunable to 0.0423 meters per second. The second customer need that needed to be met was no debris. So essentially we were preventing contamination of the atmosphere. So we quantified this by maximizing the factor of safety above 1.3. And we have a factor of safety of 1.4 for the deployment subsystem. So the calculations to determine the CubeSat departure velocity, we used an energy approach was used. The assumptions made was there is no losses due to heat. Friction is negligible as we're using a Teflon coating on both the rails of the CubeSat and the deployment, and this has a very low coefficient of friction. The change in kinetic energy of the launch vehicle is negligible because the mass is much greater. The mass of the CubeSat is 15.455 kilograms, and the spring constant is 0.5 newtons per millimeter. Using these numbers, we found that the spring needed to be compressed 8.3 millimeters to achieve a 1.5 meter per second departure velocity. So next, the failure analysis. So the CubeSat during launch creates a 622 Newton force on the spring plate. This creates a bending moment in the plate that that creates a torque in the point of interest at the end. The bending moment occurs in the pin, and as the pin twists, it creates a torque in the point of interest, at the point of interest. Using the bending moment formula for a distributed load, the bending moment was found to be 38.3 Newton meters, and the torque at the end, after it transfers through some other mechanical components, was found to be 42.3 Newton meters. And the shear stress due to torsion was found to be 0.196 megapascals. Continuing, so the bending moment at the point of interest due to the force on the spring plate was found to be 196 megapascals, and the shear force on the point of interest was found to be 1.22 megapascals. Solving for the von Mises stress, the von Mises stress was found to be 196.2 megapascals. This creates a factor of safety of 1.47, as the yield strength of T6 6061 aluminum is 290 megapascals. An FEA analysis was done on the point of interest, and it was found to be 4.73% away from the hand calculated von Mises stress, validating the results. Next, the tunability of the dispense velocity needed to be found. The assumptions are shown on the right side. Again, the spring constant is 0.5 newtons per millimeter. It is compressed to 8.3 millimeters. The uncertainty of the spring, which was found from McMaster cars, was 2% of the spring constant. And then the tolerance of the pin position was 0.5 millimeter. And using this, the uncertainty of the CubeSat velocity was found to be 0.0423 millimeters or meters per second.
Now we have the frame subsystem, whose main purpose is to provide housing for the CubeSat and maintain the structural integrity of the system. So the critical needs that it addresses are to withstand the shock loads, the harsh vibroacoustic loads, and the structural loads due to the launch environment. We evaluate its ability to do that by calculating various factors of safety for fatigue, and we find that all of the calculations exceed our minimum design factor of 2. So our calculations were performed using NASA's GEVS standards, or the General Environmental Verification Standard, particularly STD 7001, which provides the vibroacoustic testing requirements to qualify your system. Modeling the system as a cantilevered beam, we can use the material properties and the geometry to find both the spring constant and thus the natural frequency. Using this result, we will interpolate for the PSD, or the acceleration spectral density, which is like an acceleration density per frequency bandwidth. And we can calculate the peak acceleration and deflection using Miles's equations, which are basically statistical methods to find one standard deviation during a random vibration event. And so to be more conservative, we use the 3 standard deviations, or which means these results would be the maximum value is 99% of the time. And so for acceleration and deflection respectively, we have 34.7 Gs and 1.93 times 10 to the negative 4 meters. The yielding factor of safety for this deflection is 5.4 using Hooke's law. Furthermore, we have the shock response spectrum, which is provided to us by the SLS. So again, using our natural frequency of the system, we can determine that the peak acceleration due to a shock is about 336 Gs. So a shock response spectrum is basically the peak acceleration due to an impulse for various natural frequencies. And these shocks are likely due to various separation events or jettisons. So assuming a shock amplification factor of about 1.4, we can determine a shock load of 138.3 kilonewtons. And calculating the bending stress at the point of highest bending moment, we find that we have a bending stress of 40.84 megapascals, which gives us a factor of safety of about 3.52, meeting our customer needs. Lastly, we did a preliminary FEA to determine the structural loading. So SLS provided the maximum structural load factor of about 4.1 Gs for in the lateral direction, which results in a stress of about 7.298. And this gives us a factor of safety of 19.8, easily meeting the requirements for the load factors. Lastly, we have the mounting system, which is designed to interface with any launch vehicles by allowing us to adjust the positions of the mounters and the slotted members on the negative Z face. And we use lock nuts to prevent loosening due to vibrations. Its key purposes are to provide rigid mounting, adapt to any launch vehicle, and withstand shock loads. And these are evaluated either with factors of safety to prevent failure or determining how many launch vehicles it can interface with. And for each metric, we exceed our minimum factor of safety of 2, and we're able to adapt to every launch vehicle required by our customer. To withstand the shock loads, we chose grade 12-9 bolts, and we had 4 12mm diameter bolts. So from the previous analysis, we had a peak acceleration of 336 Gs, which we will use to model our force in the system. So we assume 3/4 of the load goes in the axial direction and 25% goes to the slip direction, which gives us axial and slip loads of 18.5 and 6.18 kilonewtons. This gives us load factors and load safety factors and slip safety factors of 3.41 and 2.01 respectively. Fatigue was also an issue, and so to model the system, we used again the peak acceleration from Miles' equation, which has a 3 sigma acceleration of 34.6 Gs. And if we model it as a fully reversed cyclic loading, we can use that plus the preloading, which is 3/4 of the proof force, to get our minimum and maximum forces of 60.5 kilonewtons and 62.2 kilonewtons. And with these values and using the tensile area, we can calculate both the alternating and mean stress to calculate the fatigue safety factor of 7.86 and the proof safety factor of 1.32, which is very close to the maximum possible proof load of, proof factor of 4/3.
Next, we have the control subsystem. This consists of a Rocket Labs transceiver, a buck converter, and a relay. So the first customer need that the control subsystem needs to meet is it must be compatible with bonding and grounding requirements for all launchers. All launchers used either a 61 or 37 pin connector and needed to be ground either directly to the launch vehicle or to the pins that are the screws that interface with the launch vehicle. We're using a 61 pin connector and we ground directly to the launch vehicle. It must operate at a specified voltage. This is a 28 volts for all launch vehicles, and we operate at 22 volts. We must also provide uninterrupted power. We quantified this by determining the amount of time the CubeSat would be without power, and we provide constant power to the CubeSat. So the next customer need that the controlled subsystem must meet is it must maintain mission operation for a specified time. This was specified to be 14 days. So we wanted to maximize the amount of time that the subsystem could last. We can last for 46,611 days. We must receive commands and transmit data using X-band radio. X-band radio is between 8 and 12 gigahertz. The Rocket Lab's transceiver operates at 8,100 gigahertz, putting us well within the margin. We must be able to operate in quiescent mode. We want to maximize the time to operate in quiescent mode and want to be larger than 1 year. No electronic features on our dispenser require power prior to launch, so we are well within this requirement. We must be resistant to power cycling. We quantified this by saying the CubeSat or the dispenser would be turned on and off twice a day for a year. And then we determined we can be cycled 1 million times. So the resistance to power cycling, the buck converter uses a relay, Tetherline Jam type M relay, directly from their website. The mean cycles between failure can be calculated using the following formula. X is 0.01, and this yields the 1 million cycles, which is much greater than the 730 cycles required by the customer need. Next, a common way to look at the lifetime of an electronical component is to look at how the insulation degrades over time. Arrhenius diagram on the right shows how the insulation degrades over time as a function of temperature. While 22 degrees Celsius is the max temperature we have, it's not on the diagram, but using linear extrapolation, it's found to be, the insulation is found to last 4,661 days, which is well beyond the 14 days required.
So here's our cost summary breakdown. We were able to meet the customer need of having the prototype costing less than $500. In the mass production of 100 prototypes, the reason for this price reduction stems from the OTS parts and the raw materials reduction, as we were able to purchase a large quantity of all those parts. A lot of these parts came in set quantities and packs. For example, the screws came in packs of 25 or 50. So we were able to take advantage of that. And then as far as the actual production cost, we were able to meet the customer need of having it be below $500,000 as well. A lot of the increase in OTS parts and raw materials from the production cost as opposed to the prototype cost stem from the control system. The manufacturing cost increase mainly stems from the fact that the actual production is going to require tighter tolerances. And then as far as the labor cost, there's going to be engineer salaries, there's going to be testing salaries, as well as the fabrication salaries. So overall, we were able to meet the customer need in both the prototype and the production cost.
So regarding the possibility of our concept being selected for prototyping in EML4502, we have several reasons why we believe that it should be. Number one being that we were able to meet all the customer needs in innovative ways. So the mounting especially is unique in that it is applicable to various launch vehicles, not just one, and especially the deployment that utilizes that unique release mechanism. Additionally, it withstands all of the expected loads, as was seen previously, so that we meet all the customer needs there. Additionally, those low-cost materials. So as Max just explained, how when it comes to mass production of those prototypes, we are under the that figure, as well as when we're dealing with the actual $500,000 limit, we are well within that range.
All right, so thank you so much for everybody to attending our presentation. I'd like to thank again the sponsors of MEC2, and I'd like to thank the teaching team for all the effort that they put into this class. And lastly, we want to say happy birthday to Dr. Trom.
Happy birthday.
Happy birthday, Dr.
birthday.
Sharp.
Yeah. Thanks, I think. Okay. Yeah, that's true. I turned 45 today. So yay. Except I spent the whole day watching, not that it's bad, but it's a whole day watching MEC 2 and MEC 3 presentations. So my wife actually just came home a little while ago and let me know that she's going to take me out to dinner. So that'll be a nice treat after a whole day of watching these things. But so thanks for that. Thanks for remembering. That's nice. So let's open up the question and answer period. Actually, well, Sydney's here, and then I'm here, and then Dr. Wong came in. So maybe we could let either Dr. Wong or Sydney ask the first question.
I can ask, because you didn't get Tom Singer in the full list, I can ask his favorite question I've seen so far. How are you keeping your CubeStat in place? How are you preventing it from wobbling on the rails and moving back and forth?
Yeah, I can talk to that point. So the way would be it's constrained by the door and the push plate. So we talked with the CubeSat design team to ensure that there is an imaging camera on the front of the CubeSat. However, it is recessed inside of it. So therefore, a force can be applied to both the front and the back. The back contains the rocket motors, but those are recessed as well. So there is basically a stopping point. It might be difficult to show right now, but there is a stopping point when the plate basically goes all the way back, it stops, and then the door basically shut. And once the pin puller was engaged, there'd be no way to basically rattle back and forth.
Even in 0Gs, there's nothing constraining it. There's nothing physically, like the spring plate at the in tension.
The spring plate is restrained, so the spring plate cannot move axially along the spring by the quick release mechanism. It actually interferes with it, so it can't just move back and forth.
Yeah, I would make sure you take a second look at that. Just there is some concern if there isn't like an actual constraint that your tolerances might allow for some movement. Yeah, that was basically, that's what Tom Singer would have asked you. That was pretty much my only question. So thanks, guys.
Thank you.
So probably I ask a shorter question. And first of all, a happy birthday to Matthew. It's not good to getting older. I hate to have my birthday coming nearby. But anyway, it's good for your young fellows to grow up. But for me, at least, I don't like birthday too much now. Okay, I hope Mike and Matthew still like. Okay, and also thank you for inviting me to participate, and it's good for me to hear you guys' growth or to know you guys' growth from time to time. I have a quick question. How can you estimate manufacturing cost and without naming manufacturing processes? And I see the numbers look like very accurate. How can you estimate this value, and which process will you use?
Yeah, so as far as the actual prototype process, we used a SAW. and then some milling to put the actual holes inside. That was in the prototype section.
Okay, so who can estimate the cost? I think you have a table. I probably did not pay attention to.
Yeah. So we broke it down. We could go back to that slide.
Yeah, yep. Let me
Thank you,
go back
Max.
to that.
Yeah.
Okay, I went too far. Summary. This slide.
Yeah, so we divided it by the actual materials and then the energy and the manufacturing and the labor is how we broke it down.
I see.
Yeah, no,
Okay. So
in the-
manufacturing cost is based on labor or based on what?
there's in our final report, there's a manufacturing label table. All the parts that need to be like fabricated using a milling operation, a saw cut, were based on the Gator Motorsports, like time per like or cost per centimeter cut, and that's how those calculations were made.
Okay, sounds good. Thank you, Max and Patrick. That's all
Thank
from
you.
my side. Good work, and it's a very interesting project. Thank you for sharing.
Thank you.
Thank you.
While we're here on this slide, you guys have got this labor cost 105,000 and change there. How much you paying your engineer? Well, maybe even a better question is that the overall budget is 500,000. So you're under by 200,000. Is you're still going to charge NASA the full 500, right? And you're going to take the 200,000 as profit. Is that the plan?
Yeah, split 6 ways.
Oh, good. Okay. So yeah, no, don't give the taxpayer a discount. If NASA said 500,000, charge them 500,000. Okay. So that was one. It's just to clarify that the 200,000 difference is profit. And then this 105,000 in labor, how much are you paying your engineers? I'm presuming that you guys are imagining yourselves in this role. There's, I don't know, 5 or 6 of you, maybe even 7. So how much are you paying each of your engineers for work on this?
I think we have the figures in our PDR, but I know that it was also the fabrication labor, the testing labor, as well as the engineer salaries. I know we broke it down in the PDR, but I don't know the exact values per engineer off the top of my head, but we could look at it right now.
So as you're doing that, I just did a back of the envelope. So I'm imagining the bulk of your cost is the engineering labor, not engineer labor. So I took 105,000, I divided by 6, and I get 17,500, which is what? Let's see. If I take, let's say about 75,000 divided by, let's say 17,000. Okay, so it's approximately somewhere between 4 and 5 months of no, that can't be right. Wait a minute, I did that wrong somewhere. Give me 1 second. 75,000 divided by. Oh yeah, no, I'm right. Okay. Okay, yeah, it is like 4 months of work. So is that correct? Like, is that accurate? That I mean, I guess, okay, yeah, I guess I'm answering my own question here, right? You actually took about 4 months to get this far in the process because that was the duration of the class. So okay. I'm good with this. It took me my own calculations to figure it out, but okay. So yeah, I think you guys are paying your engineers a fair salary now that I actually see the numbers. So okay, so then there was this slide. Then there was another one where you guys did a bunch of energy fluids. There was a heat transfer analysis. Several slides back that also had a fluids analysis on it.
You'd like me to go back to that?
Yeah, please, so I can see the numbers.
So.
And I noticed you guys are doing FEA, and you're super lucky Tom Singer didn't show up from Northrop, because you guys did the right thing. You did the hand calculations and then you compared against FEA, but he's getting increasingly cranky even with that, and has ripped into a couple of teams FEAs even today. So You're fortunate that he didn't come. Okay, yeah, it was this one. So, okay. So I want to come back to this in a second, but it was actually the slide after this. If I remember, maybe the slide before. Nope, it must have been the slide before. Yeah, okay. So what is this maximum effective vent ratio thing? Like, what does that mean?
Yeah, so I found that from NASA's website. It's a quantity they use to ensure no contamination, like for backflow. And it pretty much just took the internal volume and effective vent ratio. And I found that they usually set the limit around 5,000 for going into space. So I based it off that metric in order to meet the broad contamination customer need.
Okay, and how are you guys calculating internal volume? I get, but how are you guys calculating your vent area?
It's like the area of the actual check valve that goes in and out.
Okay, good. That's what I'm asking. So we have a little bit of experience from a previous reverse engineering report with check valves. And in fact, this semester, you guys have experience with the nozzles, and a lot of students were trying to calculate like water velocity out of the nozzle, and discovered that the cross-sectional area that we thought was the area that the water or the minimum area that the water traversed through actually was not, right? So that's what I'm asking. I've seen other groups calculate this ratio and just use the hole in the bulkhead, not the actual cross-sectional area of the valve. So, okay, so that one's good. Heat transfer analysis. You talk me through this a little more. What's I see T initial and T final. So this is some sort of transient.
Yeah, it's really just to find the temperature to ensure that the thermal customer need. I just thought that using the basic heat transfer equation with the total heat that would enter into the system could get us this value, which was able to justify the range that we needed for the temperature.
So, okay, what's the initial so you're imagining the CSD is sitting on the launch pad, and that's the initial temperature, and then you launch the rocket, and now you're out in space and 22 Celsius.
And the ascent profile, because I think this need goes to the ascent profile, so it's during ascent. So pre-ascent and then.
Okay, what's driving Q then in that case? The total heat in the system.
The ascent, the launch.
This is just for the CSD, right?
Yeah.
Yeah. So like, what's there's like electronics that are generating heat, or the CSD is somehow conducting or convecting or radiating to the walls of the launch vehicle.
Yeah, I mean it's just from the actual ascent profile that generates the heat. That was the assumption I made when I used this equation.
I think the SLS official paper had it was a graph that graphed the whatever that's why Max keeps saying ascent profile. It's an ascent profile graph of the thermal load in the SLS rocket.
Okay. And it's given in.
Thank you.
It's given in Q, like it's given in watts. Or I guess Q is not watts. Q would be joules. It's given in joules.
Yeah, the heat generated.
Huh. Okay. Yeah, that's weird. So okay, that's not how I would have done it, but maybe I could talk to you guys offline and see what it was that you did. So I guess the way that I'm interpreting this equation is there's some thermal energy that basically gets transferred to the CSD during this ascent process, and you don't have numbers in here other than the final temperature, but that heat transfer is some number that's given by NASA. They say like anything that's sitting in the SLS co-manifested payload compartment is just receiving I'm going to make up a number, 100 joules of energy. Is that how they give it to you?
And there was a temperature range from this heat that was generated, and I thought that the heat transfer equation could effectively allow us to quantify that range based on the ascent profile.
Yeah. Huh. Okay. Okay. This the reason that I'm kind of picking on this one is because I've seen a lot of heat transfer analyses over the course of this week, and I'm not sure that any of them was correct. But this one is different than so in all the other cases I've had, the student teams have basically done a radiation heat transfer analysis. And they're imagining that the CubeSat, not the CubeSat, the CSD is out in space, and they're trying to figure out like how, well, in some cases how hot it gets, but in most cases how cold it gets. And they're having it radiate basically to space at, somewhere between 2 and 3 Kelvin. And what's at least in my opinion, what's wrong with that is that it's actually housed inside, the CSD is housed inside the launch vehicle. So you're not actually radiating to space, you're radiating to the walls of the launch vehicle, which themselves probably aren't, 2 or 3 Kelvin. So anyway, that's why this one kind of struck my interest, because this is a different approach than I've seen. So you're basically doing a transient heat transfer. So what are you guys using for like mass and specific heat? Just the CSD or the CSD plus the CubeSat?
I did the CSD plus the CubeSat.
Okay. Yeah. Okay. That's what I would have done. Yeah. Okay. All right. So I'll stop picking on this for a second, and let's see. Can we go to, there was a Bernoulli. I think it was the next slide. Maybe it was the previous slide. Yeah. Okay. There we go. Okay. So this is your.
Hello guys, sorry, I needed to sign off, and hopefully you guys enjoy your discussion with Dr. Trump and Sydney, and enjoy your education at UF. Good luck, guys.
Thank you so
Thank
much.
you.
Thank you, Dr.
Thank
Long.
Appreciate it.
Thank you.
Thank you for coming.
Thank you. Good luck. Go Gators.
Raiders.
All right. Thank you. Okay. So back to Bernoulli here. So ideal gas law, I think, is fine, right? Because we're basically talking about air or vacuum, right? Somewhere in between. So it's definitely going to behave like an ideal gas. So that's okay. What is it that we're actually calculating here? This is, you're trying to find the pressure as a function of time inside the CSD?
Yeah.
It was
Exactly.
given to us by the aerospace students. They've just said, I don't remember the number off the top of my head. They
It
said
had
the
to be-
depressurization rate
It
during
had to be
something.
less than negative 0.3 psi per second.
Okay. And that's probably some sort of like decompression limit, right? It's you don't want to, I mean, you guys have all seen the like the space horror movie, right? Where like, the airlock opens up and like, people start exploding and stuff because the pressure change is too severe. So that's probably what it is. So just that number, that minus 0.3 psi per second number, was given by the aero team, or is it this entire analysis?
They gave us the value that we had to meet. It had to be less than negative 0.3 psi per second.
Okay, gotcha. And then so you've got you say with assumptions, and so the assumptions are the velocity inside the CubeSat is much smaller than outside, or the through the vent, right? That's what that VE is the velocity through the vent. And then that the pressure on the outside is basically zero, right? Which is that's okay, because it'll be slower than that, right? If you're going through ascent, right? You're going to pass through like regions of the atmosphere that aren't necessarily zero pressure, but that are reduced pressure below like 1 atmosphere. So your vent rate is actually going to be slower, which is good to prevent decompression. Is it right that V, what you guys are calling VI, internal velocity, it can be assumed to be 0? Is that a good assumption here?
I mean, I made the assumption because I assumed it was much greater, much less than the external velocity. So I removed it, and it didn't have much of a difference solving with or without it, and it helped simplify the iterations.
Yeah, I think so. This to some extent goes back to that venting ratio that you showed before, right? It's if you have so imagine, right, so now we go all the way back to thermo. You've got this like really big chamber, right, and it's got this really small like outlet port. And in that case, if the chamber is really big and the outlet port is really small, then if you draw a streamline far enough into the chamber, the velocity is going to more or less be 0 in the chamber as it's venting. But I'm not sure that that's true here, right? You guys have a relatively small internal area, and not a pinprick type port cross-sectional area, but something bigger. So I guess what happens if that assumption is not correct? Like, does the situation get better or worse? Like, is this, I guess where I'm going with this is this a bounding calculation where you can say it's actually better than this rather than does it get worse?
Yeah, I mean, I just didn't see it having much impact when I calculated it. So because it had to go through the iterations, I decided to remove it and use it as an assumption. But I'm not sure if there could be a greater impact. But within the analysis I did, it seems safe to make this assumption.
Yeah, I'm not sure. There's definitely like a thermo problem like that looks at this and actually looks at that hole size and the vent hole size. And there comes a point where the hole gets small enough that you can do this, but I'm not sure that you guys are there yet. So anyway, okay. That's just another little nitpicky fluids thing. Okay, so I've asked you guys about the labor. I've asked you about the heat transfer of the fluids. Let's see, maybe if we could just run quickly forward through the slides. I feel like there was one more thing, but I'm forgetting what it was.
While you're looking, I just had a couple comments for the team.
Oh yeah, go ahead.
Put your numbers on your slides. That's just something that you should be doing. That's something that you're going to be asked to in industry. Other thing, great job announcing your credentials at the beginning. That's what your investors want to hear. They want to hear why you're the people to do this job. Yeah, so that was great. And then for your calculations, you're going to want to show your numbers, like where your final answers are being derived from. It's not helpful to us because we just see the final thing and we have no idea how you got there. So yeah, otherwise, excellent. Great job, guys. So that was my main points. All right.
Thank you.
I remember sorry guys. I remember my question, which is, this is my last one, which is you guys were talking about actually, so this is sort of general because I think it happened a couple times, but you guys are talking about like a 14-day lifespan. I remember it specifically when you were talking about the insulation on the wires, right? Which that was a cool, I've never seen anybody do that. Like that, what did you guys call it? It was like a
Arrhenius plot. I had to do a lot of digging to find something that I knew or any like that I could perform that calculation for. So.
Yeah. So kudos on finding that and doing that, because that's I've not seen any other group do that. I didn't even know there was such a thing as wire lifespan. But so the comment that I was going to make though is in a lot of cases, you've got like a 14-day lifespan, and then your system can survive for like 10,000 days, right? And if you know there's the analogy in the race car world of as your race car wins the race, it sort of drives over the finish line and falls apart as it's driving over the finish line, right? And that's considered like the optimal situation because you've designed it like just well enough and you've gotten the weight down as far as you could possibly get it. and just to meet the bare minimum requirements to finish the race. And so when you guys are like doing these calculations and you're finding, my customer need statement says 14 days and I get 10,000 days, is your system over designed? Like, is it too good?
For that, I don't think so. I think all wires will last that long. It was just, as it gets hotter, they won't last as long. That might not have been the best analysis for it, but that was all I could find. So it's not like we're going out of our way to purchase higher quality wires or higher quality electrical equipment to meet this need. This is just what the standard was for a normal set of wires.
Gotcha. Okay. So you'd have to, you'd actually have to try pretty hard to find something that would be a wire that would die in 14 days. And it might even be more expensive to find such a thing. So, okay. I gotcha. Okay, cool. I think I'm done. I'm out of questions. So Sydney, any others?
None for me.
None? Okay. Well, this is probably a good place to wrap up. Plus I'm looking at the time and I'm like physically incapable of ending class on time. So that trend continues through the final presentations. We're about 5 or 6 minutes over. Want to just close by thanking you guys one more time for sharing your presentation with us and your design with us this evening. And depending on who you ask, it's either a Mech 2 or Mech 3 is considered the final boss of the mechanical and aerospace engineering curriculum. So according to John Brooks, it's Mech 2. So at least by John Brooks' measure, you guys have survived the final boss of the curriculum. So congratulations on making it all the way through. And we recognize that it's a lot of work, right? It's a 3 semester credit hour class that should probably be 6 semester credit hours. So we recognize that and see you guys working hard and appreciate the time and energy and enthusiasm and especially patience with me that you guys exhibited all semester to get to this point. So thank you again for that.
Thank you.
Thank you, Dr. Trump.
Thank you.
Thank you.
Great. Okay. My last thing is remember to fill out your course evaluations because we've got like about 30 hours left. So please do that. There's an extra credit opportunity if enough of the class submits those. So don't forget. Okay. With that, let me hit the record stop button.